Okay, ready when you are.
Okay, fantastic. So thank you very much for inviting me to give a talk. Special thanks to the organisers for setting up such an interesting Splinter session. And I'd like to say especially thanks to the speakers in this Splinter session so far, because it's made my job a lot easier because I don't have to repeat some of the basics of lithium depletion. So sorry I can't be with you in person, at least to set my background to San Diego Zoo, so at least I'm there in spirit. Okay, so I'd like to talk with you about lithium and rotation today. So what is the lithium rotation connection? Well, this is an observed phenomenon amongst K stars in coeval clusters that essentially it seems that the faster rotating stars for a given mass seem to deplete less lithium. So this has been observed in many open clusters, and the relation has been known for a few decades now. And on the right, you can see some of these plots of the delta equivalent width versus rotation period, where we see this, this relation. As pointed out by Lyra before, there are several competing theories as to why this might be the case. So I won't have time to go into that, but we can talk about that later if you like. So this data, these examples have all been for individual clusters, so kind of like single projects working on one cluster at the time. And they all point to a lithium rotation connection, but it would be useful to see if there was a homogeneous sample where we could really measure the lithium over several clusters. So what do? Well, it's quite simple. We have to measure lithium equivalent widths in many clusters. We need to measure rotation periods from somewhere and then simply put it all together. And that's all there is to it. So step one, measure the lithium equivalent widths. And as George has described very well in his talk, we take our data also from the Gaia-ESO survey. And our parent sample consists of 24 clusters, aged between 1 and 600 million years. And they're all relatively close by because we need to have a good shot at measuring the rotation periods, as we'll see later. So as you can see, the colour magnitude diagram of the targets on the right-hand side. In total, we have approximately 400 high probability members that have been selected based on the kinematics from Jackson et al. 22. So a quick note on measuring the equivalent widths. We could have taken the data directly from the final catalogue of the Gaia-ESO survey, but it does turn out for a lot of the targets with low signal to noise, there is missing data, and maybe it's difficult to deal with upper limits as well if we want to have a look at this lithium rotation connection. In addition, there seems to be a slightly troubling offset in the M stars, particularly for clusters around the Pleiades age, where there seem to be measurements of around 100 to 200 milliangstroms, where surely we would expect this to be around zero because the lithium should have depleted by then. So what we did, thanks to Richard Jackson's code that he provided, is we downloaded the ESO spectra, we used non-members as template spectra for a given color, and then we fit the continuum using that template. And as you can see, the red marks here for Blanco 1 at around the Pleiades age suggest that we've at least fixed this offset. So this is the data we'll be working with. This is what the clusters look like with the Eagles isochrones overplotted, so we don't have to go any further into that. Okay, second step is calculate the rotation periods. So here's where I want to introduce the software that I've developed in the past year or so. It's a tool called the Tessellator. So the aim of the Tessellator is to provide the user with just one command line prompt, which will then allow the user to download test data. It quantifies contamination by looking at neighboring Gaia sources. It then runs its own aperture photometry on the pixel files. And then we do some light curve fixing to that. So there's a normalization, detrending, and cleaning process, which is specialized for the test data. Then we run a periodogram Lom's-Gargle analysis, phase-fold the light curve, produce some quality criteria from the outputs, And then we can measure a final rotation period from multiple sectors. Okay, so we had 40,000 Gaia-ESO light curves, and we ran this using a kind of batch process here on the Baden-Württemberg clusters, and it only took 24 hours. So I feel like we have quite a powerful way of measuring lots of rotation periods quickly with the tessellator. We just submitted this paper too. If we have a look at those periods versus things that have been seen in the literature before, we find around 75% that lie on the equivalence line. It started to feel a little worrying that there was some disagreement on either side. But when we look at the light curves, we find that when the literature predicts a short rotation and TESS predicts a long rotation, the light curves do appear slightly on the longer side, around 5 to 10 days. On the other hand, where we measure short rotation periods and the literature is long, we do look like we are getting evidence of short rotation in these as well. So hopefully this lends confidence to the rotation period method. Now, the way we selected the final rotation periods is, well, effectively by choice, by human choice by now. We hope to use a more advanced technique perhaps in the future, but this is very much a preliminary work in progress. So let's have a look at when we put the lithium and rotation together for some of these clusters. So I may need to describe this diagram for a second. So we have the classic lithium equivalent width versus color on the x-axis. I split this into 4 different spectral type bins, as you can see, for K stars and M stars. The red crosses are lithium measurements where there is no rotation period available. The truth is there's quite slim pickings with TESS because some of these targets go down to G equals 90th magnitude, where the signal to noise is just too low in TESS. And then the blue circles, the filled circles, are TESS rotation period measurements that are scaled so the faster rotators are larger. The green lines are linear fits for those given spectral type bins. And the game that we're playing here is we want to measure the delta equivalent width compared to the rotation period. So how far from the line, in each case, is the equivalent width measurement. And we want to just highlight the ones that have a statistical significance of less than 0.1. Okay, so the p-value less than 0.1 here. So this is a new cluster. This is Alessi 43 at an age of 8 million years. And we can see in the early M stars that there is indeed a kind of a strong connection here in the M0 to M2 stars where the lithium is undergoing depletion and may undergo rapid depletion soon. But that was an interesting find. We kind of replicated the same findings that we got for gamma Vel a couple of years ago in Binks et al. 22, where we find that again for the early N-type stars, we have this clear trend that the faster rotators are less lithium depleted. Then we have some clusters at a slightly older age, like N2547, where we wouldn't expect any lithium in the M stars now. However, in the mid-K stars, we recover that classic connection. And finally, in Blanca 1, around the Pleiades age, we see in the early K-type stars, again, the same kind of connection for K0 to K5. We can place this data as well into age categories. So on the y-axis is 3 different age bins for a given cluster. And you can see on the x-axis the kind of spectral type range. The blue section here that's covered is just where we expect full depletion in the lithium, so it's fairly meaningless this side. But what we can see is when we bunch the data together, we do get quite a few clear correlations for the lithium rotation connection. But interestingly, we do get for the early N-type stars for the first time the same connection. So just to summarize, we've used the Gaia-ESO data to study the lithium rotation connection for several clusters. I've just highlighted some of the prime ones there. We have now rotation period measurements for just over 1,000 of these cluster members using TESS rotation periods. It seems that the lithium rotation connection is indeed unilateral amongst K stars when it's observable. And we seem to have found for the first time in the early N-type stars amongst the young clusters that there is also this lithium rotation connection that is matched to what we see in the K stars. Okay, so that's pretty much everything. I'll just leave the advertisement, if you like, there for the GitHub link to the tessellator. And I'd like to take the time to answer any questions. Thank you.
Okay, so Marina Kunkel is asking what fraction of cluster members get rotation periods measured from tests?
What fraction from the high probability members? In the end, it turned out around about 25% of the high probability members had what I would call reliable test data. So with this, we've used some of the quality indicators to actually screen out a lot of the kind of low signal to noise data and things that are particularly noisy and difficult to measure. So most of these are around 13th to 16th magnitude in G. As we go to fainter magnitudes than that, it's quite difficult to get any kind of signal, but in certain clusters, we are fortunate and we can go slightly deeper.
All right. Thank you, Alex.
Thank you.